Today, I am going to discuss some of the relevant questions and the pattern of the subject matter with respect to KCET. Here, I have taken and selected the topic called solids. As we know, the solids are mainly categorized in two types, crystalline and amorphous. The major part of this chapter deals with the crystalline solids, which have the compact and the systematic arrangement of particles. Their study is undertaken with the help of the unit cells and also the crystal lattices. Further, the arrangement of the particles is taken up with the help of the close packed structures, and in these close packed structures we may have the perfect and the imperfect crystalline solids. Based upon their nature and based upon their properties, we have some of the very important practical applications like the conductors, semiconductors, and the magnets, which we always use in our day-to-day need and in our everyday life. Here we go with some of the relevant questions which can be seen in the competitive examinations as the multiple choice questions. It doesn't mean that whatever the questions we discuss here, they will be the ones which appear in the examinations. Even if we prepare for thousands of questions, the examination carries the question paper with a question altogether different from this. It is only an attempt as to how these questions can be approached and how they can be interpreted to the best of our ability. We shall make our sincere attempt in this regard. Here we go with the first question. Among solids, the lowest melting point is exhibited by. The four options given are covalent, molecular, ionic, and amorphous. Basically, we say the solids have the high melting points, but in the crystalline category, we have four types like molecular crystalline solids, ionic crystalline solids, covalent crystalline solids, and the metallic crystalline solids. Among them, the molecular crystalline solids have the lowest melting point because of the weak van der Waals forces, while other three are with the fairly strong attractive forces, carry the high melting points, and about the amorphous solids, they do have the high melting points. Therefore, our correct option is supposed to be the molecular crystalline solids, that is B. In the second, which of the following shows good electrical conduction? Here, we turn on to the crystalline solids, again the 4 types. But remember one thing, among the 4 types, only one is having the electrical conduction, and that is the metallic type, because of the free movement of electrons. While other 3, they don't have the free movement of electrons, nor they have the free movement of ions. Therefore, sometimes we may find little bit confusion, like as to pick up the pure common salt or a gold ring. Pure common salt is a solid. The particles are held in the fixed position and the ions are unable to move, and electrical conduction cannot be observed. While in the gold ring, the metallic solid, electrical conduction is observed. Then sand and ice are the covalent, and the molecular crystalline solids, they also don't possess. Thereby, our option comes with the gold ring, that is C. In the next question, one more property that we see in the crystalline solids is anisotropy, a very peculiar and characteristic of the crystalline substances. In this, some of the physical properties, not all, like the refractive index, when measured in different directions, the value of this property will be different according to the directions we select. That is due to the systematic arrangement of the particles in crystalline solid. And here the question goes as, anisotropy is observed in case of the 4 options: plastic, glass, rubber, and common salt. Immediately, we focus upon the common salt, because it is a crystalline substance, and for the crystalline substance, anisotropy is the characteristic, while the first 3 belong to the amorphous category, wherein the glass requires a special attention because it is considered as the supercooled solid and supercooled liquid, and it is the amorphous. Therefore, as the crystalline substances, we pick up common salt for this question as correct option. The next, number of brevis lattices. Look here. We go for the study of the crystalline solids with the help of the crystal lattice and the unit cells. These are the basic requirements for the crystalline solids, where we say a lattice is 3-dimensional pattern of the points showing how the particles are arranged in the crystalline solid. And these points, if are to be studied individually, it becomes a difficult task to complete the entire study of the crystalline solid. Thereby, we pick up the smallest and the repeating unit that we see in the lattice. This unit is supposed to possess all the features of the lattice. That is why the study of the crystalline solid and its crystal lattice is made with the unit cell. There are 7 basic unit cells we observe, and these 7 basic unit cells are: number 1, monoclinic; number 2, triclinic; number 3, tetragonal; number 4, hexagonal; and number 5, orthorhombic; number 6, rhombohedral; and number 7, cubic. 7 unit cells. 7 unit cells provide us the 7 lattices. Look, any crystalline substance we get, whether it is a laboratory prepared sample or naturally occurring material, its lattice should match with one of these 7 lattices built up from the 7 unit cells. Therefore, they are supposed to be taken as the standard lattices, and these standard lattices are called as 7 crystal systems. And these 7 crystal systems are further subdivided into the spatial lattices. For example, the cubic unit cell, it has 4 types, like simple cubic, body-centered cubic, face-centered cubic, and edge-centered cubic. It has 4 subtypes of the unit cells. But in some others, we have 1 or 2 or even 3. Therefore, totally out of the 7 crystal systems, we get the 14 space lattices. And these 14 space lattices are called as the Bravais lattices. Now the question, it becomes so simple that the number of Bravais lattices are 7, 10, 14, 21. Immediately, we put the option with respect to C, reading 14, because there are the 14 Bravais lattices built up from 7 crystal systems. In the next question, we observe the way in which these particles are arranged. What are the number of particles which are in contact with a given particle? Look, anyway it is the packed substance, packed material. The particles are closely held. If we take the systematic arrangement of the particles, we find these particles in the form of layers, and the layers are placed one above another to produce the 3-dimensional crystalline solid. In that, if we pick up one particular layer, the layer which we place horizontally can appear this way, and there we are. One particular particle at the center, it is having the nearest neighbors 6 in number, and this 6 becomes the coordination number. And about the coordination number, remember one thing, totally it carries the different statements or different considerations in coordination compounds and in crystalline solids, where in the complexes or the coordination compounds, we attribute this coordination number to the number of coordinate bonds. In the crystalline solids, we go for the number of nearest neighbors. The number of nearest neighbors are 6 here, and coordination number is 6, and this is controlled by the value what we call as the radius ratio. It is simply the ratio of the radius of cation to the radius of anion. As this value increases, the coordination number increases. Now look, with the radius ratio value between 0.155 to 0.225, we have the coordination number 3, and 0.225 to 0.414 gives the coordination number 4, and 0.414 to 0.732 the coordination number has to be 6, and from 732 onwards almost nearer to the value 1 the coordination number will be 8. And these are the 4 ranges with which we have to be quite familiar. 0.155 to 0.225, number 3, 0.225 to 0.414, number 4, 0.414 to 0.736, number 6, and 0.732 onwards, it is the coordination number 8. And therefore, the things become as easy as we can hope for. The radius ratio 0.24, 0.36, 0.51, 0.93, there we have to select the coordination number 6. Naturally, the selection falls upon the option number or option C, that is 0.51. So please make a note of it, like what are the basic needs we do have in the study of the crystalline solids, that is their compact arrangement and their melting points and their physical properties like anisotropic nature, systematic arrangement, and the coordination number of each of these particles in the crystalline solid. And we will be going for some more questions where we explore some of the other features of the crystalline solids. So friends, we pick up with one more question. The crystal system of a compound with the unit cell dimensions, make a note, A equal to 0.39, B equal to 0.39, C equal to 0.65, given in nanometers, and the angles alpha, beta, and gamma equal to 90 degree is. So first of all, what is meant by A, what is meant by B, and what is meant by C. About the unit cells, the dimensions for the unit cell, we can see here, it carries the length, it carries the breadth, it carries the height. Length is given with A, breadth is given with B, and height is given with C. And the angles, we call them as edge angles, alpha, beta, and gamma. Alpha is the angle which is seen between the breadth and height, and beta is the angle which is seen between height and length, and gamma is the angle which is seen between length and breadth. With the help of these edges and the edge angle, those 7 basic unit cells are developed, like the monoclinic, triclinic, tetragonal, hexagonal, orthorhombic, rhombohedral, and cubic, like that. So here we elucidate the unit cell and its crystal system this way. If the A equal to B, length and breadth are equal, but the height is unequal. A is equal to B and not equal to C, while all the angles are equal and equal to 90 degree. And this is nothing but the tetragonal system. So tetragonal system is something which can be visualized with the unit cell of this type. It carries the length and breadth in equal dimensions, but the height is unequal, that is the value of the C. Angles are equal and equal to 90 degree, and therefore our option goes with tetragonal unit cell and tetragonal crystal system. And here, one more information that I would like to pass on to you is about the cubic. Some are very simple to remember and carry on with further informations. Cubic is the one where we say all edges are equal and all angles are equal and equal to 90 degree. All edges, length, breadth, height equal. All angles equal to 90 degree. While the last, that is the triclinic, here we have the total opposite characters. All edges are unequal, all angles are unequal, and they are not equal to 90 degree. One, the most symmetrical cubic, and another, the most unsymmetrical triclinic. Coming to this orthorhombic, here we have length, breadth, and height, the edges. Edges are unequal, but the angles, alpha, beta, and gamma, they are equal to 90 degree. Can you recall such a type of the geometry in some of the day-to-day used materials? Like it is the matchbox. In the matchbox we see length, breadth, and height are unequal, but the angles, they are equal. So that is how the 7 unit cells are individually distinguished with the help of the length, breadth, height, and the angles present in between these dimensions. Then we come to next question. Sodium and magnesium crystallize in BCC and FCC type crystals. So what is the BCC and what is the FCC? BCC is the short form for body-centered cubic lattice, and FCC is the short form for face-centered cubic lattice. And these lattices have their own unit cells, which we popularly call them as BCC unit cell and FCC unit cell. And the unit cells of these two metals here, the BCC and FCC type crystals, the number of atoms of the sodium and magnesium in these unit cells. So how these number of atoms or number of particles can be calculated in the unit cell? Now look, calculation becomes very, very simple. For that, we have to remember these 4 types of the lattice points which hold the particles in the unit cells. Number 1, it is the corner lattice point. Number 2, it is the body-centered lattice point. And number 3, face-centered lattice point. And number 4, edge-centered lattice point. Contribution-wise, we say corner particle makes a contribution of 1/8 towards that unit cell, because that corner is going to be shared with the other adjacent unit cells. One corner, one unit cell, 1/8 contribution. While the face-centered lattice point, it contributes 1/2 of the particle to that unit cell, because a phase is being common to two unit cells. Therefore, per phase, per unit cell, contribution will be 1 by 2. And the edge-centered particle, it is making the contribution of 1/4 towards the unit cell, because the edge is common to 4 unit cells. It has to be shared among the 4 unit cells. Per unit cell, the contribution works out to be 1 by 4 particle, while the body-centered lattice point, it makes the contribution of only 1 particle, entire particle to that unit cell, because that particle is not going to be shared among other unit cells. This way. BCC unit cell, if observed in sodium crystal, and what that BCC unit cell is, see here. This is the BCC unit cell having the corner particles as well as the body-centered particle. This is the body-centered particle. Now the calculations are very, very simple. From 8 corners of the unit cell, the number of particles will be 1, because it is 1/8 from one corner, and into 8 from 8 corners, the particle is 1. Body-centered particle, it is a particle of that unit cell. Therefore, in case of the sodium, the number of particles is 2. While in the magnesium, which comes in FCC type unit cell, face-centered cubic unit cell, that unit cell is shown with the 6 faces carrying the additional particles at their centers, and of course, the corner lattice points are common, and they are a must. So here, from 8 corners, the number of particles will be 1, as in the previous case. This is the contribution from 8 corners. And from the face, each face contributes 1 by 2 particle. 6 faces will be giving a total of 3. So the number of particles in the FCC unit cell is 4. Thereby, Na carries 2 particles and Mg carries 4 particles in its unit cell. And there, we can easily go for the option 2 and 4, that is the D. This way, the particles can be worked out.